Okay, so we know what monotonic sequences are now, or monotone sequences. They're just sequences that either always increase or they always decrease. And so now I want to prove the first big theorem about monotonic sequences, which is that if you go back, or if you watch the first part of this lecture, I gave a bunch of examples of monotonic sequences, right? And towards the end, I went through and kind of pointed out which ones were bounded and which ones weren't bounded, okay? And if you might have noticed actually, and maybe if you didn't, you could go back and check, but each of the bounded monotonic sequences was also a convergent sequence. And obviously the unbounded ones, any unbounded sequence can't converge because we know that all convergent sequences are bounded, right? So that's actually the content of this theorem, which is just that for a monotonic sequence, it's enough to be bounded to force the monotonic sequence to converge, okay? And this is actually a pretty powerful result. And you should sort of appreciate this because for arbitrary sequences, boundedness is an extremely weak condition, right? Like there are many bounded sequences which don't converge. For example, -1 to the n, or like cosine of n pi over whatever, any of these oscillating sequences, or just any random, sequence of a bounded sequence of numbers won't converge, okay? So it's a very powerful, basically monotonicity is a very powerful condition on a sequence, and it forces it to be very well behaved. So I'm going to state the theorem. This is theorem 10.2 from the book. All bounded monotone sequences, converge. Okay. Now, when it comes to proving this theorem, you should be sort of, it should be not obvious, probably, how to proceed, right? I mean, if you've gotten used to the way that we've dealt with convergence so far, right? Remember when I introduced the concept of convergence, I kind of like talked a lot about the structure of a proof when you're trying to prove a sequence converges, right? Which is what we're trying to do here, right? Let me just like start, I'm gonna write the first two sentences of the proof. Oops. So let Sn be a monotonic sequence. Okay. In fact, actually, sorry. Let's focus on monotonically increasing sequences. The proof doesn't really change for increasing or decreasing. It's just there's a very minor adjustment that you make. So if I show it to you for the increasing sequences, hopefully you'll kind of see how to do it for the decreasing sequences. So let's say, and also we should make it be bounded. So be a bounded monotonically increasing sequence. Okay, so Sn is our bounded monotonically increasing sequence, and we want to show it converges. Okay, now remember, so what I was saying is I've talked a lot about what it looks like when you try to show a sequence converges. You have to let epsilon be greater than 0 or whatever, and then we want to choose n, right, and so on. Okay, now here's the issue. Well, first of all, how can we proceed before we've even talked about what the limit of the sequence should be, right? In here, you're supposed to say what the limit is, okay? So this is a strange example. So in all the previous examples, we've had some handle on what Sn actually looks like. Usually we'll have like a formula for it or something, right? And so then we just calculate what the limit is, and we either give it as like an algebraic expression or oftentimes just like a number, right? And in this case, we can't do that because there's so little we know about Sn. The limit could be anything in a sense, right? So let's just think a little bit about what the limit is. What is the limit of Sn? Okay, let's kind of visualize Sn a little bit, okay? So I'm gonna just sketch it here. So we have maybe some point, you know, here, and then it increases a bit, you know, maybe it increases a little bit after that, maybe it increases more after that one. But ultimately, right, remember that there's some upper bound, okay? Actually, let me erase some of these points to give myself a little bit more room here. So, you know, these jumps could be kind of random. Maybe it stays the same here, and then maybe it jumps again. Sorry, that's supposed to be the same. It's not supposed to decrease, obviously, right? So here's some upper bound. So basically, if we look at this picture, what would we guess is the limit, right? Well, it looks like the sequence might be approaching this upper bound, right? So we might guess that this upper bound was the limit of the sequence. But here's the problem. We don't know just from this picture whether the sequence actually goes all the way up and basically, you know, reaches the upper bound. Like if it gets arbitrarily close to the upper bound, it might get, there might actually be a smaller upper bound, right? Like maybe we picked a bad upper bound in the beginning that was too big. There could be a smaller upper bound that the sequence gets closer to, right? And so this kind of suggests that, you know, that really the unique number that this sequence tends towards is not just any upper bound, right? Obviously, the limit has to be an upper bound because the sequence is increasing. But it's not just any upper bound, it has to be specifically the least upper bound, okay? So actually, let me erase this. Actually, we should guess off the bat, even before we formulated the proof in its entirety, we can actually just like, not just guess, but we can essentially know just from this kind of, just from thinking about it a little bit, that the supremum of all the values in the sequence should be the limit. So take S equals the supremum of Sn, not the absolute value. Sn for n, you know, in n, if we're assuming that it's indexed by the natural numbers or whatever indexing set it should be here, we're just taking the supremum of all the values, right? This is the, remember, it's the least upper bound on the values of the sequence. Okay, so we can kind of confidently pick this limit and expect the proof to work out somehow. But now we have to think about why this actually is the limit of the sequence to formulate the proof, right? Well, let's let epsilon be greater than 0. So now we want to pick big N somehow, right? So the question is, so I'm going to sort of redraw the picture over here now. So the question is, how do we make sure that Sn gets within epsilon of S? So let's, there's some good news here. So let's say this is S, right? So then there's that, you know, there's the band of S plus epsilon. This is S plus epsilon. And then there's, you know, S minus epsilon, right? And so the question is, how do we make sure that the sequence stays within this band, okay? Well, there are two things we can kind of notice right off the bat, right? First of all, the sequence will never be outside of the band on this side, right? In fact, the sequence will never be above S, right? So this whole sort of area we can kind of ignore, right? We're not worried about the sequence being greater than S, okay? So really it's just we want to get the sequence within this lower bit. So basically, so what I'm saying is instead of trying to force the absolute value of Sn minus S to be less than epsilon, we can just force Sn to be in between S minus epsilon and S. So instead of Sn minus S less than epsilon, just need S, sorry, just need S minus epsilon to be less than Sn less than S, right? This is a minus sign. So we just need to get Sn to be in between S minus epsilon and S. That's enough, because obviously that forces this to be true, okay? But we don't have to worry about sort of dealing with this absolute value or anything. We can just make this be true instead, okay? It's better to think about it this way. And so then the other thing about it is that actually, if we find a single value, so let's say our sequence is here, right? And it's increasing or whatever, right? In fact, well, actually, let me redo that a little bit. So yeah, let's say the sequence is like this, and then, you know. So now, right, okay, look, we found a value that's like inside the band that we want, right? But now how do we make sure the sequence stays in there? Well, actually, if you think about it, there's nothing we really have to do, right? Because now, since the sequence has to keep increasing, it's not actually allowed to jump out of this band again, right? It has to keep going, okay? So the question is, so this is what we need, okay? Now this is where we use the fact that S is the supremum specifically, right? I mean, we have to use something about what we know about suprema, because otherwise, you know, we could have just taken S to be a random number, and you know, there couldn't. So there's no way to complete the proof without using something of our knowledge of what S is and what suprema are, right? So I'll lay it out now. All right. So because S is the least upper bound of Sn, S minus epsilon is not an upper bound, right? And we've seen this before too, remember? So take note of this, remember this, that whenever you have a supremum, one of the most useful things you can do with it is you can know that any number that's smaller than the supremum is not an upper bound, okay? So what that tells you is there exists some capital N such that S capital N is in between, oh, actually, so S minus epsilon is in between S capital N, or sorry, S capital N is in between S minus epsilon and S, right? That's exactly what we wanted over here. So this is basically S capital N in this picture, right? So then for n greater than n, right, S minus epsilon is less than S capital N, which is less than or equal to S little n, which is less than S. So clearly S little n minus S is less than epsilon, which is what we wanted, right? Because S little n is in between S minus epsilon and S. That is enough to say, I mean, it's actually stronger than this statement here, but it definitely implies that S little n minus S absolute value is less than epsilon, right? So that's basically the proof. I mean, that's the proof for increasing sequences. And then, of course, for decreasing sequences, I mean, maybe it would be actually healthy for you to just think about how you would modify this proof. Yeah, I would say it's almost exactly the same, just with a couple, a couple things change. Obviously, the choice of S changes, and then some of these inequalities get flipped. But that's basically it. So that's the proof of convergence for monotonic sequences. And then in the next video, we'll talk about, well, we'll do some examples, and we'll talk about divergence, and then we'll get to the limit superior and limit inferior.